Alright, so in the last video we looked at the iterative formula, and we said when we're using the iterative formula we stop when we get two iterations that have the same value correct to the specified degree of accuracy. So when this happens, we say that our sequence of approximations has converged to that value or that answer that we get. So you're going to get a lot of questions that say, show that if a sequence of positive values by the iterative formula converges, then it converges to alpha. If we read through the question, the equation called f x is equal to 3x as one real root in the interval x is between 0 and pi, denoted by alpha. We know that alpha is the root of this equation. So part B is saying, show that if a sequence of positive values by the iterative formula converges, then it converges to alpha. So what they're basically trying to tell you here is to say that alpha is the root of this equation. So show that this iterative formula is the same as this original equation, that equation that produces alpha. Alright, so we just basically, so we have to prove that this iterative formula is the same as that. We can start with our iterative formula and remove the n plus 1 and all the n's. This is x is equal to 1 over 3 x plus 4 arctan of 1 over 3x, and our goal is to show that this is the same as quote half x is equal to 3x. So to do that, let's start by multiplying through by 3 to get rid of this 3. So that's 3x is equal to x plus 4 arctan of 1 over 3x. And let's subtract x from both sides so that we've got 2x is equal to 4 arctan of 1 over 3x, and divide both sides by 4. So you get 2x over 4, which is 1 over 2x, is equal to arctan of 1 over 3x. And let's apply tan to both sides. So this becomes tan half x is equal to, the tan will cancel out the arctan, so equal to 1 over 3x. And our goal is to make 3x subject of the formula. So this becomes 3x is equal to 1 over tan half x. And we know that 1 over tan x is quote x. So this is 3x is equal to quote half x. And if you really want to be specific, we can put the quote half x on the left, and this is equal to 3x. So we've shown that this is the same as the equation in part A. So because this iterative formula can be reduced to the original equation in part A, it means that if this iterative formula converges, meaning that if we carry out our iterations and get an answer, that means it has converged, and that answer that it gives is the answer from this equation, which we are calling alpha. Alright, let's see another example of this question. So here we're given, part A says, by sketching a pair of suitable graphs, show that the equation x to the 5 is equal to 2 plus x has exactly one real root. Alright, we're not interested in solving that, we just want this equation here. Anyways, part B says, show that if a sequence of values given by the iterative formula xn plus 1 is equal to 4x to the 5n plus 2 over 5x to the 4n minus 1 converges, then it converges to the root of the equation in part A. Which is to say, if this iterative formula gives you an answer, then that answer must be the answer from this equation. So we have to show that this iterative formula is the same as the original equation. So let's start with our iterative formula and remove the n plus 1 and all the n's. So this becomes x is equal to 4x to the 5 plus 2 over 5x to the 4 minus 1. We can start off by multiplying through by 5x to the 4 minus 1 to get rid of our denominator. So that becomes x times 5x to the 4 minus 1 is equal to 4x to the 5 plus 2. So let's expand the bracket that we have on the left. X times 5x to the 4, that's 5x to the 5, x times -1, that's negative x, is equal to 4x to the 5 plus 2. Our goal here would be to make x to the 5 subject of the formula. So let's put all the terms that have x to the 5 on the left and everything else on the right. So that's 5x to the 5 minus 4x to the 5 is equal to 2 plus x. So this gives us x to the 5 is equal to 2 plus x. So we have shown that if the sequence of values given by our iterative formula converges, then it converges to the equation in part A.